welcome back to the course Cobots Theory and Practice. So we were in week 3 transformation matrices and robot kinematics. So in this lecture we'll discuss on kinematic transformation, especially rotation matrix operator. We'll extract rotation matrix. We'll discuss on rotation about x, y and z axis. We'll move ahead with order of transformation. What would be the effect of changing the order of transformation? We'll discuss what is orthogonality. We'll discuss rotation about an arbitrary axis, and finally we'll end up with Euler angle representation, that is a kind of rotation representation. So everything is about rotation in this lecture. So let us begin with kinematic transformation, especially rotation matrix operator. In the last lecture we discussed translation matrix operator. So kinematic transformation, rotation matrix operator. Let us say there is a point P with position vector OP. O is the origin and it has three projections along orthogonal axes, that is Px, Py and Pz, or you call it N, O and A. Okay. If at all it is rotated about x axis by certain angle theta, okay, so N remains where it was, but it comes out of the axis y and now it is O, and similarly A comes out of the axis z and by an angle theta again, okay, so it becomes A. Okay. So this is how it will look once it is rotated about x axis. Okay. So we are looking for a transformation matrix which can actually do that. Okay. So let us say there is a vector PUVW, that is here, this is PUVW, this is the vector. Okay. And I apply a rotation transformation matrix on it and it gets rotated about the axis x, y or z. So rotation about the origin of the fixed reference frame. So over here x, y and z is the fixed reference frame, okay, whereas rotating reference frame is UVW. Okay. The point is now represented in XYZ frame. Now after rotation we want the new location of the point to again be represented in XYZ frame. So PUVW is the initial vector that needs to be rotated using a transformation operator over here, and it should now be represented in XYZ frame. Again the rotated position of this should be rotated and represented again in XYZ frame. So now let us begin extracting the rotation matrix which can actually do that. So PUVW is the vector which is shown here. Okay. It is given by PU, IU, PV, JV, PW, KW. What is I, J and K? They are orthogonal vectors, unit vectors along the axes of the frame, which is the rotating frame. Now by definition of scalar products, the components along x, y and z, let us say it gets rotated by an angle theta about x axis. So it comes to a new location, u remains where it was, and v and w actually comes out of the x, y, z axes and a new position is attained. Okay. And this time O and A are the vectors which is actually making some angle with initial y and z axis. Okay. So again this point P, this position vector OP will have projections along x, y and z after rotation, and those will be given by projection of PUVW, that is this vector along x. So that should be given by PUVW dot Ix. Okay, I am taking the projection of PUVW along x, so I am taking dot product Ix dot PUVW. Okay, so this actually gives me the projection along x axis. So this is the first thing that I do to get the Px. So, the projection of P UVW along x. Similarly, I could get Py by taking dot product with Jy, okay, and similarly Pz can be obtained by taking dot product with Kz, okay. So, this time Ix, Jy and Kz are the unit vectors along x, y and z axes, okay. So, now this vector I will substitute here, and what I get is Ix dot Iu into Pu. Pu is the magnitude of P along U. Similarly, Ix Jv, Pv, Ix Kw, Pw, and same goes along each of the axes x, y and z, okay. Rearranging this in the matrix form will now give me Px, Py and Pz, that is the projection of the vector P UVW along x, y and z after rotation, okay. These were the projections along x, y, z that existed before rotation, and that was also equal to PUVW, PU, PV and PW. So, what essentially is this? This is the desired rotation transformation matrix after rearranging this that I got is actually doing what I intended to do. This becomes the operator which is applied to PUVW and gives me the rotated point P about x axis by an angle theta, and same can happen. It can be rotation about any axis because this is a general transformation. I made it explicitly along x axis so as to explain it, but yes, this can be a combined rotation about x, y and z axis, anything, okay. So, and this becomes the general rotation matrix, which is an operator which is applied to PUVW to give you the new projection of the vector P, okay, PUVW. So, this is the vector after rotation, it gave me the projections along x, y and z. So, effectively this is the new vector after rotation, okay. So, now this becomes my rotation operator. This is my initial point before rotation and this is the point after rotation. Rotation about x axis. How to obtain that? I want to rotate about x axis by an angle psi, okay. So, what I will do here, you see Ix is not changing, Ix remains aligned with Iu, okay. So, Iu remains wherever it was earlier before rotation. What changes is V and W, okay, that goes off by an angle psi, okay. So, now if I substitute Ix is equal to Iu in this is the general rotation matrix. So, angle between Ix and Iu is 0 degree. So, those two are unit vectors. So, Ix dot Iu will give you 1, angle between them is 0 degree. Now, let us look at Ix and Jv. Ix is here, Jv is here, angle between them is 90 degree, should give me 0, 0, 0 and 0. Now, let us look at Jy and Jv. You see there is an angle, that is psi over here. So, Jy and Jv, if you take dot product, should give you cosine of psi. Similarly, Jy and Kw, okay, Jy and Kw, okay, this one Jy and Kw. So, there is an angle here Jy and Kw. So, 90 degree plus psi, it should give you minus sin psi. Similarly, this is sin psi and again cos psi. What we obtained here is rotation matrix operator which will rotate the frame and it will bring it to a new location, that is rotation about x axis by an angle psi, and it will take to this, okay, this new position. So, this way you can apply it to a point and that point can get rotated by an angle psi about x axis, okay. So, this is the rotation matrix about x axis. Similarly, In order to rotate about y axis, you can substitute, you go back and see what you can substitute here. Next time you have to substitute jy is equivalent to jv. Okay. If you substitute this again here and apply the similar technique, you just check their angles should be 0 degree, 90 degree or the required angle, okay, angle of rotation. Okay. So, over here it is phi, okay, that angle is phi, and that can now be seen as this. So, this becomes my new rotation matrix, which is when applied to PUVW can give me a point in XYZ frame, that is a rotated point by an angle phi about the axis y. Similarly, rotation matrix for z axis may be obtained like this, and this time it is rotation about z axis by an angle theta. Again the angles between the vectors would be 0 degree, 90 degree or angle theta. The substitution could be kW is equivalent to kz. Okay. So, that should be substituted to this equation again, and you get to the rotation matrix about z axis by an angle theta. Rz theta when applied to PUVW gives me a point XYZ, PXYZ. Okay. So, this was my initial position of the point. So, that point is now rotated about z axis by an angle theta and gives me the new point. Okay. So, this is what it means. In terms of 4 cross 4 homogeneous transformation matrix, it can be written like this. So, whole of this 3 cross 3 matrix comes to this location without any translation part over here. Okay. This is pure rotation. Okay. So, this is the physical meaning of that. So, P when applied with rotation matrix operator goes to a new position P dash, that is rotation about z axis by an angle theta. Okay. So, now you see this is the initial point applied with 4 cross 4, this transformation matrix gives me the rotated point, which is this. Okay. So, this is the new location of point P in the initial frame XYZ frame. Got it? Okay. This can also be obtained using geometrical method also. Okay. So, now composite rotation matrix. Let us say there are multiple rotations which are happening one after the other about x axis, about y axis, about z axis or in different order. So, that can go like this. So, finite sequence of rotations are arranged in a way like first rotation comes first, second rotation will come here, third rotation will go here. They are pre-multiplied. Okay. Because let us say this is the point, you applied a transformation matrix 1 here. Okay. This gives you a new point P dash. Okay. This is applied with next rotation matrix, okay, and this gives you a new point P double dash, and again this is applied with a third rotation matrix and this takes you to the final point P triple dash. Got it? So, every multiplication is a operator on the previous result. So, that is why it is one after the other applied about the same reference frame. So, that is the reason it is pre-multiplied one after the other. So, order goes like 1, 2 and 3. This time it is Rx alpha, rotation about x axis by an angle alpha, that comes here, rotation about z axis by an angle theta, rotation about y axis by an angle phi. So, that comes here. If you multiply that, you get to this. Okay. So, you can try changing the order, you should get a different result, we will discuss that. So, in order to do such calculations, you can easily use symbolic computation toolbox, which is there in the MATLAB also, or you can use MuPad. Okay. Wolfram Mathematica you can use, which is for Windows, Raspberry Pi or Android platform, WX Maxima, which is there in Ubuntu also. You can use any of these symbolic computation tool in order to do this kind of complex multiplication, need not to do by hand. Okay, so you can try changing the order. Okay, so what you see here, by changing the order, let's say you applied Rx first and then Ry on PO. So what would happen here? Let's say this is the initial orientation of this book. Okay, rotation matrix is all about orientation changes. First you rotate about x axis by an angle using the right hand thumb rule. You should be doing this. Okay, it comes to this. Next it is rotated about y axis by 90 degree. So this should be here. Again it goes like this. Okay, by an angle 90 degree, final orientation is something like this. Now if I have changed the order, I did y first then x, what would happen? The first rotation about y axis, y angle 90 degree, it comes to this. Next rotation is rotation about x axis. So I'll do rotation about x axis by angle 90 degree, and it comes to a new location which is like this. So you see, by changing the order of rotation operator, what you got? You got two different orientations. That means rotation matrices are not commutative. In general, matrix multiplication is not commutative, and changing the order will take you to a different state. Now let us recall our matrix which look like this. So rotation general matrix applied over PUVW point, which was the initial position vector, gave me a PXYZ point. Okay, that is a rotated point. Okay, or a position vector or a vector. Okay, so this is my initial point, this is the rotated point. Okay, about certain axis, whatever is told by this rotation operator. Okay, so now let us assume there is an operator which is inverse of this. So let us take it as Q. So what is Q? It takes you otherwise. Actually PUVW was here, PXYZ is here. In this time it is inverse, so it is PXYZ here and PUVW here. Essentially this should be equal to R inverse of this. When I take inverse, I got to this. So if you take this, calculate this, you should be getting this. I just rearrange this, I got this, and as dot product is commutative, you can rearrange. Okay, you can flip this values which are here. Okay, and what I found here is this, essentially this matrix is R transpose. So what I found here, I started with taking inverse of rotation matrix. I just rearranged it assuming dot product to be commutative, and I got to R transpose. That means Q is equal to R inverse is equal to R transpose. So what is it? This is basically is a matrix. So R is a matrix which is an orthogonal matrix. For orthogonal matrix, R inverse is equal to R transpose. That is what is the meaning of this. So what we have found here is rotation matrix is an orthogonal matrix. So please note, these are few points. If the rotating coordinate system OUVW rotate about one of the principal axes of OXYZ frame, then pre-multiply the previous resultant rotation matrix with appropriate basic rotation matrix. What does it mean basically? Again, I'll come back to this. So if this was my initial point PUVW, I applied a rotation matrix, it gave me PXYZ. So this was the meaning. If there is second rotation which is again about base reference frame, that is X, Y and Z, again we are doing rotation. So if this is the first rotation matrix, the second one will come here. Okay, why is it so? As I have explained earlier, the second rotation is happening on top of the result of the first rotation. Whatever this gives me a new point PUVW dash. So rotation 2 is happening on top of this. So it has to come before. If I open up the bracket, it comes as R1, R2. Okay, like that. So it says you have to pre-multiply the previous rotation matrix with the appropriate basic rotation matrix. R1 is the first one, R2 is the second one. Okay. Now, if the rotating coordinate system rotate about its own principal axis, then post multiply the previous resultant rotation matrix with appropriate basic rotation matrix. Now, this time what does it mean? Let us say this is your initial frame x, y and z. This was your point. Now, you have rotated the point from here and it went to a new location here. The second rotation is not about the base rotation matrix. This time it is with respect to the rotated reference frame. Okay, wherever it is standing, it has rotated, it came to a new point. From there you did another rotation. From this location you did another rotation, not again with respect to the principal frames, you did rotation with respect to the new frame after the rotation. So, first rotation has happened, from there you have rotated again by certain angle. So, this time it would be a post multiplication. So, rotation 1 and you post multiply and that becomes your second rotation, and this case it is in relative reference frame, not in absolute reference frame. Okay. Now, this would happen even in case of 4 cross 4 matrix. So, irrespective of 3 cross 3, 3 cross 3 in these two cases, it could also be in 4 cross 4. That means 3 cross 3 sub matrix can remain here and translation will go here and these will be 0. Okay. So, using 4 cross 4 also these two rules apply. Inverse of a rotation matrix is equivalent to its transpose. We have seen rotation matrix is orthogonal matrix. There are still many other rules that you can notice while we discussed rotation matrix. Coming back to that, let us say you just take up with any rotation matrix. Okay. So, all these elements are basically component of same vector along x, along y, along z, and that vector was a unit vector. So, each of these column represents a unit vector. Okay. This is a unit vector, this is unit vector, and moreover the next to next rows, okay, this row to this row, angle between them is 90 degree, this is 90 degrees. So, all the consecutive rows are orthogonals also. Okay. This is orthogonal to this, this is orthogonal to this, and this is orthogonal to this. Okay. So, one by one they are all orthogonal to each other and each column is a unit vector. Now, let us see how these rotations that we did now is rotation about the base frame, that is rotation about the base x axis, about y axis or z axis. Let us say I have to rotate about any arbitrary axis in space, not about x, y or z. How to go for it? So, this is the method for this. So, rotation about an arbitrary axis, I will do that now. I will find out the rotation matrix which actually can do this. So, in order to do that, what we tend to do here is R is the unit vector with components Rx, Ry, Rz. So, let us say this is the axis about which I want to rotate. Okay, I want to rotate and this passes through origin O. Okay, about this I want to do the rotation by certain angle. Okay, how to do that? We just derived rotation about x axis, rotation about y axis or rotation about z axis. This has a component, this R vector has a component Rx, Ry and Rz along the principal axes, that is x, y and z. okay, and this vector passes through origin. Okay, steps would be, we'll try to align R after consecutive rotations to one of the principal axes. Okay, in this case I choose to be along Z axis, so I'll do in steps few rotations so that R gets aligned to Z axis here, and I'll do the rotation and I'll bring back to the original state. So what I'll do here, in first step I'll rotate about x axis by an angle alpha, okay, so as to bring this R vector in zx plane. So this comes here after rotating like this. So this is my first step. Okay, hope you could follow this. Okay, so now again there is second rotation. This time I have to rotate about y axis by an angle minus beta. Minus or plus is governed by thumb rule, that is right hand thumb rule. Okay, so this time I have to rotate about y axis by an angle minus beta. Okay, this side is positive, this side is negative. So you see, by doing negative beta I can bring the R, which was in first step it came to zx plane, now it should get aligned with this. Okay, so now R comes finally along z axis. Okay, now I will do the desired rotation, that is rotation about z axis by an angle phi. So this is the desired rotation. So what I did, I brought R from here to here and finally to here, did the rotation. Now I have to bring it back to the original location, because what I have is rotation matrix about x, about y and about z. I don't have an rotation matrix to rotate about arbitrary axis or any other axis. Okay, so I did it and then I will bring it back. So now what I will do, initially what I did, I rotated about y by minus beta. This time I will bring it back by an angle beta. So rotation about y by an angle beta, I will come here and I have to go back to this location, okay, where I was. So in order to do that, I will do rotation about x axis, okay, by an angle minus alpha this time, and I come back to initial location R. So this was done in 5 steps, rotation about x by an angle alpha, rotation about y by angle minus beta, doing the final operation, actual desired operation that comes here, and bringing it back to the initial location. So these are the 5 operations. Mind it, all the rotations were happening in the principal axis, so it has to be pre-multiplied. So let me first find out the angles also. Using simple trigonometry and the projection, I can obtain the angles also. R was the initial position vector about which I wanted to rotate. Okay, so this is R. So components along x, y and z will be Rx, Ry and Rz. So R is known, so Rx, Ry, Rz is known. I have to find out angles alpha and beta, cosine and sine A, because you know rotation matrix has components of sine A and cosines only, all the elements. So yes, sine alpha will be Ry by this root over Ry square plus Rz square. You can find it out. So this is your Ry, okay, that is what you know, okay, and that becomes this essentially. And how much is this? This one, this is Ry square plus Rz square. So this is Ry and this was Rz. So Ry square plus Rz square will give me this. Okay. So that is it. So alpha is obtained. Similarly, cosine alpha, sine beta and cosine betas are obtained. R, magnitude of R is unity. Okay, that gives rise to, let's say in denominator it comes as Rx square plus Ry square plus Rz square. So it should give me 1, okay, because it is a unit vector. Okay, so now all the operations can be written in steps like this. This was first, this was second, this was third, this was fourth, this was fifth. So order would be like this, because all the rotations were with respect to the global frame. So now if I put them all here, so cosine alpha, in short I have written it as cos alpha. Similarly, sine alpha, I have written it as S alpha, and they can be put in this order. So this is rotation about x by alpha, rotation about x, cos minus sine, sine cos. Similarly, rotation about y by minus beta. Okay, all the matrices are arranged this way. Upon taking product of them, I got to this. So where v phi, it is versine phi, is equal to 1 minus cos phi. Okay, so wherever you find v phi, it is actually equal to this. Okay, so this is a combined rotation matrix which can directly be multiplied to the initial point so as to rotate about arbitrary axis given by Rx, Ry, Rz, that is the R vector by an angle phi. Okay, so P can now be transformed using this rotation matrix. Okay, so there are many other methods to do such tasks. That few of them are quaternion, Rodrigues matrix, direction cosine. So other methods also you can do this, but this is one of the simplest one which you have just covered. Okay, because it is very simple and we had enough background to come to this result. So I have used this. Okay, now rotation representation. Let's say your robot end effector is at a state. I want to represent how is it. So there are multiple ways to reach to the same point. You have seen maybe a sequence of rotation Rx, Ry, Rz can lead you to there. There can be relative transformation also. Okay, that is what we'll talk about here. So how to represent such rotations. Okay, so rotation representation are generally done using Euler angle representation. It reduces requirement of 9 elements of rotation matrix for specifying rigid body orientations to 3 angles phi, theta and psi. Okay, so using any 3 rotations you can get to any particular orientation. So there are standard techniques to do that. There are total 24 such combinations which are possible using absolute rotations, that is with respect to the global reference frame, and combination of global and local reference frame. What does it mean basically? There is an object in space, okay, you have rotated about global frame, about x axis, about y axis, about z axis, and you reach to a certain orientation. You could have done rotation about x axis and then rotation about current reference frame, wherever it is now, from there you rotate again, and from new you rotate once more. That means first was with respect to global frame and remaining two were with respect to relative frame, wherever it is, from there you rotated. Okay, so there is a reference frame which is known as gyroscopic system 1. It tells rotation about OZ, that is the global frame, by an angle phi. Then rotation about local x axis, that is the object frame, by an angle theta. Again rotation about object frame W, UVW is the object frame, XYZ is the global frame. So U and W finally, psi angle about W frame, okay, local Z axis, that is W. Okay, so global, local, local. Okay, the next one is again rotation about phi, about Z, theta, V, that is local, local y and local z. This was local x and z. Okay, this is gyroscopic system 2, ZVW. Okay, and the third one is the most simplest one, that is most widely used also because of its simplicity and easy to understand. Okay, it is rotation about x axis, about y axis, about z axis, that is roll, pitch and yaw rotations. That is all three were about global frame, not about the object frame. Object frame basically means there is a frame which is attached to the object. The object in its own frame can rotate about its x-axis, about y-axis, like that. Okay, so that is what I mean. So wherever it goes, so when you do the first rotation, all the axis changes. So from there, about the current x-axis or y-axis, it has further rotated. Okay, so that is what is the local rotation. Okay, now let us talk about Euler angle system 1. What was this? It was Z, U and W by an angle phi, theta and psi. So Z, U and W by an angle phi, theta and psi. Okay, now let us see how does it work. So initially U, V and W was aligned with x, y and z. Okay, after first rotation, that is rotation about z by an angle phi, you see U comes to U dash, V goes to V dash by an angle phi, phi. Okay, W remains wherever it was. Okay, in the second operation, I have to do rotation about U, that is the local frame, by an angle theta. So where is my U? U is here. Okay, so rotation about U, so U dash will remain wherever it is because the rotation is about this axis itself. So V goes to V double dash by an angle theta, W comes to W dash by an angle theta. So new locations are this. Okay, now rotation about W by an angle psi. Okay, so this time rotate about W by an angle psi. So W will remain wherever it is. V comes to V triple dash, U comes to U triple dash. Okay, these two basically gets changed. So this is my angle, this is my angle. So this is how after 3 consecutive rotation, 1 global, 2 local, okay, that is the local reference frame, it has rotated and it has come to a orientation. Okay, so final orientation, that is the outcome of 3 rotations, is given as this. Final rotation matrix would be like this. You see, because first one happened here and next two were local. So effectively those two are post multiplied, not pre multiplied. Second local transformation, third local transformation. First one was global. Okay, so order is like this, it goes like this. Okay, if I put all the matrices here, so this is the first global transformation, then next local and local, phi, theta and psi, z, u and w. Okay, z, u and w, mind it, z and w becomes different. Initially they were aligned, but after even a single transformation about any of the axis, w comes out of z. Okay, and now z becomes the local frame. Okay, so the order is this, this and this. Okay, that is global, local and local. This gives me this. Okay, irrespective of this, same orientation can be achieved by a different approach. It could be, this is equivalent to rotation about principal axis of the reference coordinate system as rotation of phi about z. So this looks like this is rotation about z axis by an angle phi, is it not? This is exactly the same matrix. Okay, next one is rotation about x axis by an angle theta, and the third one is rotation about z axis by an angle phi. So, you see it is in reverse order, global, global and global. Okay. So, if I could rotate about global, global, global and reach to the same orientation, I could have easily done this. Okay. But in this case gyroscopic system, and it is global, local and local, 1, 2 and third transformation. Okay. So, there are at least over here you have noticed there are at least two ways to reach to the same orientation which is given by this. Okay. So, this operator when applied to a point, it can give me rotation about x, z, u and w. It can take you to a particular orientation, or you can represent the orientation of the object using this. Orientation would be given by this matrix. Similar is system 2. This time it is rotation about z, v and w by an angle phi, theta and psi. You can work it out quite easily here. So, initially it is rotation about z axis by an angle phi. Okay. So, phi here and phi here is visible, this goes here. Next operation is about v, okay, about v by an angle theta. Okay. So, this comes out by an angle theta, goes by theta, and the third one is about w by an angle psi. So, about w by an angle psi, this comes out by psi further and further. So, final orientation is given by this, this and this. These are the final orientation of the system. Okay. So, again it is global, local, local, that is system 2. Only difference is instead of x, local x, it is local y, that is v over here. Okay. This again can be written like this: global, local, local in post multiplication way. Okay. So, rotation about z axis, rotation about y, rotation about z, but because it is local, it came post multiplied form. So, you reach to a particular orientation. Again this is equivalent to principal axis rotation. You can write it as global, global, global. Instead of global, local, local, you can have global, global and global. So, order would be reversed. How much it is? It is rotation about z by an angle phi, it is rotation about y by an angle theta, it is rotation about z by an angle phi. Okay. It will take you to the same orientation. Okay. This is Euler angle system 2. There are 24 such combinations combining global, local, local. Maybe there are many such ways you can arrange it. There are total 24 such combinations which are possible. Okay. The best one what I find, which is most widely applied also, is roll pitch yaw system, that is Euler angle system 3, and that is very conveniently used in case of any floating objects like aircraft, marine vessels, mobile phones. These days you have accelerometer in your mobile where you can play games, head mount device, quadcopters like this, Formula 1 cars, industrial robots to effect and effector pose you can express. So, all these uses roll pitch yaw type of combination. In this case all the three rotations are with respect to global frame. So, rotation about x, rotation about y, rotation about z, they are known as roll pitch and yaw axes. So, this is x, this is y, this is z. So, roll, pitch and yaw axes. This is shown with respect to ship, but it is also applied with many other floating based systems. Okay. If you write them in matrix form, so this is your rotation about x axis by an angle phi, y, theta, z, psi. phi theta psi. Okay, multiply them, you get to this. Okay, again this can be expressed as global, local, local. Okay, that's all for this lecture. In the next lecture, we'll discuss on robot frames, DH parameters, link transformation matrix, and we'll do forward kinematics. That's all for this lecture. Thanks a lot.